right, good morning and welcome to section 2.4 where we're going to talk about exact differential equations. So, recall if we have a function z that's in two variables with continuous first partial derivatives, then its differential looks like this, where we take the partial differentiation with respect to x and y of our function. Well, if f of xy is equal to c with a constant, we get the partial of f with respect to x dx plus the partial of f with respect to y dy equals 0. If f of xy equals c, we can generate a first-order differential equation by computing the differential of both sides of the equality. So, here's our example. If we have x cubed minus 7x plus y squared equals c, so here we have a function in two variables which is set equal to c, and we want to compute the differential on both sides, so we're going to do partial derivatives. So what we would do is we take the partial of our function with respect to x dx plus our partial of our function with respect to y dy, and in this case we're going to get 0. So if we did this problem, we take our function and take the derivative with respect to x, we'd get 3x squared minus 7y dx plus the partial of our function with respect to y, which is going to be negative 7y plus, negative 7x plus 2y with respect to y, and that equals, and then some constant, which when we take the derivative, that would be 0. So that's what our equation would look like if we took the partial derivatives. Now, the thing is, and this is the question, this right here, x cubed minus 7xy plus y squared, is a solution to this differential equation. All right, we worked this out and we took the derivative, so this is a differential equation. And what we want to do is there a way to go from here back to there? All right, and that's what we're going to focus on today, where we're given an exact equation, which is an equation that we had to do partial differentiation to get back to an original equation that's in terms of both x and y. So, an exact equation. A differential expression m of xy dx plus n xy dy is an exact differential equation in a region R of the xy plane if it corresponds to the differential of some function f of xy defined in R. A first-order differential equation is of the form m of xy dx plus n xy dy is equal to 0. It's said to be an exact equation if the expression on the left-hand side is an exact differential. So, how can we check whether our differential equation, m of xy dx plus n of xy dy, is an exact differential? Well, this is how we can figure that out. Well, if I have m of xy, one thing I know is that it's with dx. So what I had to do is I had to take the partial of the original function with respect to x. Also, if I have n of xy, that function that's with my dy, then I know that in order to get my function of n, it was going to be the partial of f with respect to y. Now, if I recall from Calc 3, I know that if I'm taking the partial derivative of f with respect to x, and then I take it again, but with respect to the other variable, which is y, that should equal the partial derivative of x with respect to the partial derivative of one that I've already taken with y. So if these two equal each other, then they came from the same potential solution, or they came from the same equation. So what we're going to do in order to check to see if they are an exact differential, we're going to take m, which we already took the derivative, which is already the partial derivative with respect to x, and we're going to take that with respect to y. And we're going to see if that derivative is equal to n, but we're going to take n, and we're going to take that partial derivative but with respect to x. If those two equal each other, then we have an exact differential equation. So this comes from kind of Fubini's theorem when we're talking about partial derivatives. I don't know if you recall when we took the partial of x and took the partial with y, it's going to equal if we took the partial of that then with the partial of x. And so that's how we can check. All right, and now I'm going to quickly go over how we're going to do this, and then I'll say that to next example.